How is everybody? Great. It's almost Friday. So, anyone going to the big game this weekend? Ha, ha, ha. No one's going to the big game this week. Unless you're on the team. You're giving out water bottles or something for the team. So, yeah. Anyone have big plans for the weekend other than watching the game? Woohoo! Congratulations! He's getting married on Saturday. Where at? Right, Jordan River Temple. Oh, that's fantastic. Congratulations. For your wife, what's her major? Electrical engineering?
What?
Your algebra homework?
You done?
Oh, she has a math minor. Nice. Well, you know, my dad always said, you can marry more in 5 minutes than you can make in a lifetime. So, I don't know if you're doing that strategy, but. We do have a few problems here for you to be thinking about. So, I don't know if I just messed up what you were doing, Porter, but. Oh, is it just, are we sharing just a window and not the screen? So. Anyone else have big plans? None of the plans seem as big compared to, you know, getting married. No one's playing a marathon game of Dungeons and Dragons with their roommates. So, yeah. Okay, well, let's get started. Who'd like to offer a prayer for us? Thank you.
Our Father in heaven, we're so grateful to be gathered here at this time. We're grateful for the opportunity to learn more of the workings of the universe that Thou hast created for us. Father, we ask you to bless us with understanding and bless us with Thy Spirit to accomplish Thy will. We ask these things in the name of Jesus Christ. Amen.
Amen. Thank you. Okay, homework is over here. You have to read more of 3.5, read up to the definition of dimension. Luckily, the department office is just down the road. You call that number, have them bring another battery or another mic. Okay, not for me, for the next person. Okay, so read 2 and including the definition of dimension. What's 3.5b video? I'll make that after class today. And then do the web assign 3.5b. Don't forget. And then do the written for 3.5a. I am changing one of the written problems. So number 9, it says prove something in R3. You can do it in R2 if you want. It shouldn't take as long, and you'll still learn what you need to learn, I think, if you do it in R2. So, okay. Oh, and the exam. So the exam is going right now. It ends tomorrow night, 11:59 p.m. Do not talk about the exam, please, even after you take it. Or I guess what are you going to talk about before you take it? After you take it, do not talk about the exam. Don't talk about it until after you get the scores back, okay? The reason is that usually there's always 1 or 2 students. Something comes up, they end up in the hospital, you know, they're a family does, whatever it is, emergency, and they don't end up taking the exam in the allotted time, and they have to take it later. And if people show up in class the next Tuesday, and they're talking about what's on the, I've had this happen in my class, where they show up the next day, they haven't taken the exam, and everyone around them, they're talking about what they wish they would have known on the exam and which problem was hard and stuff like that. So don't talk about the exam. I've also had students talk about the exam. One of them was my student, a calculus exam. They're just outside the doors here, while other people are in here studying for that exam, and they're talking about the exam and what problems are on there, what they wish they knew, okay? Don't talk about the exam at all. You can tell people how long it took, okay? That's it. Don't say, oh, it was hard, so hard, okay? Oh, it was easy. Don't say stuff like that, okay? Just, oh, it took me 3.5 hours, okay? And good luck. So, helps keep things fair that way. See, anything else? Yes? 2 hours. Yeah. So it's written to be a 2-hour exam. So, or if you took one of the practice exams and sat down and took it under testing center conditions, then it'll take you about that long. So, okay. So I'm going to show you something I wish I would have showed. I meant to do last time, or last week, not last time. Oh, there we go. Although it didn't, we had problems the first time, and I'm sure we're going to have problems again. I don't know what it is about this computer. It does not like my Excel spreadsheets. So you can use matrices to create codes and to decipher codes. And the way you do that is you write down a code. Here's the code. Pick me up at tilde. Someone in the other class, maybe there were a few people in the class, they didn't know what this symbol was called. So I said it was a tilde. So we changed the code to say pick me up at tilde. So, and for every one of the characters, there is a number associated with it. So down here, you pick either a character, you can find the number in the middle here, or if you pick the number, you can find the character next to it, okay? So I can take any code I want, and I can translate it, I can turn it into a set of numbers. And then what I do is I pick a number, like 3 or 4 or 5, how big I want, and then I just start chunking up that code. So I picked 3 this time. So I picked the first 3 numbers, and they become the first column of my matrix. And then I pick the next 3 numbers, and they become the next column of the matrix. And then I pick the next one. They become the next column of my matrix. Okay. And so I can make a message matrix that way. So it still says the same thing. You just have to read it down like this. You just have to read it like Chinese, except they go right to left. Right? You go top down, left, right to left. I can't remember. Okay, so this would say, pick me up at tilde. So, and then how do you encode that? I'm going to pick a matrix. And if I chunk them up the code 3 at a time, I'm going to pick a 3x3 matrix, but it has to be invertible. And I'm also going to pick it to have whole number values, because then all these are whole numbers. if I pick it to have whole number values, then I know when I do the multiplication, I'm going to end up with whole numbers again. So, if I take this is my encoding matrix, and I multiply it by this matrix, I get this, and this is my encoded message matrix. This is something I would just pass to people. So I'd pass to my friend, but I'd have to give them the decoding matrix or give them the encoding matrix, and then they could find the inverse of it. And so to decode that, I'd multiply this one by this one. That's what we tried to do before, and it didn't work. I do not know why. So it should be this one. Comma. This, but it didn't do the matrix multiplication. See, it only does the first one. So I don't know what's wrong with this. It works in my office. I should just bring whenever I do Excel, I should just bring my own computer and do it on my own computer instead of here. So, but this only works if you have an invertible matrix. If I change it to a non-invertible matrix, so if I change that to 3, now it's non-encodable, I can still multiply this encoding matrix by the message matrix, and I can still get an encoded message matrix. But why can't I decode that? It is non-invertible now. But what is it about this message? It looks almost the same. Why can't I unencode? Why can't I decode this encoded message matrix? Ryan, what were you going to say? I don't have a matrix to multiply by, and the reason I don't have a matrix to multiply by is because this 3, 1, 3, 5, 27 in here, there's lots of different matrices that I could multiply by and get this 1693 where it started from. I'm sorry. There's lots of different matrices I could multiply by this 1693 and get 31, 35, 27. And so I don't know which one of those to use. So if it's an invertible matrix, there's only one. There's only, if I have 3, 1, 3, 5, 24, then, and I know the matrix, then I had to come from 16, 9, and 3. But even if I know the matrix, even if I knew that matrix and I knew this was 31, 35, 27, I don't know if it's 16, 9, or 3, or one of the infinitely many other things that it could have been to get me 31, 35, 27. Because that free variable, or 2 free variables that I have, caused me problems. Okay, so this was a really important, this used to be really important. It is breakable now. A more complicated version of this was what the Germans used and what the Allied powers broke. Their Enigma machine, we broke the code, and it shortened World War II because we were able to do that. So, okay. Take a minute and look at this. I know some of you already have. Take one more minute, think about these things, and then I'll talk about them. All right, what are we thinking about number 1 up there? Well, the first one, I didn't number it. We have vectors in standard position in the first quadrant. So both the coordinates of each of the vectors, they have to be 0 or greater. Is this a subspace or not? So I'm just going to have you do thumbs up if it's a subspace, thumbs down if it's not a subspace. Okay, thumb sideways if you don't know. Okay, so go ahead. Give me what you want. Give me what you think. Thumbs up, thumbs down, thumbs sideways. For the first one. Yeah, for the first one. So, okay, I see lots of thumbs up, a few sideways thumbs, a couple thumbs down. Well, let's go through and check. So is the 0 vector in our subspace? So here's our coordinates. Does the 0 vector, 0, 0, 0, if x is 0 and y is 0, does that satisfy our set? Is it still in this set? It is, yep. So 0 is in there. 0 vector, check. Is it closed under addition? Can we, if I take any two vectors in there and I add them up, do I still get vectors that will have this property, where the x coordinate will be greater than or equal to 0 and the y coordinate will be greater than or equal to 0? Yeah, if I take any two numbers that are 0 or greater and add them together, I'm going to get 0 and greater. So it is closed under addition. Check. Right, I can't. There's no way by taking two vectors in here and adding them together and ending up over here, over here, over here. Right? There's no way. So how about, is it closed under scalar multiplication? I see some heads going like this. I see some heads going like this. Okay. What scalar is going to cause us problems? A negative. If we multiply, like if I take this one and multiply by a -1, where does it go? So it's not closed under scalar multiplication, because now we're getting vectors that are outside that set. We started with a vector inside that set, multiplied it by a scalar, now we ended up with a vector outside that set. So, okay, if you have a partial subspace like this, the way you can expand it till it's a subspace is just take independent vectors and take the span of those. So in this case, since we're in 2 dimensions, you take two independent vectors, take the span of those, and that'll complete a subspace. So closed under, oh, I should do scalar multiplication. No. Okay. All right. Someone in the last class asked a question about, what about subtraction? Don't we have to worry about checking to see if subtraction works? And because you can get this with a subtraction, it's 0 minus this thing. But we don't have to do that, because once you have these two things, you have all possible linear combinations. And so we already have u plus a minus 1v, because if v is in there, then a -1 times v is in there, and if we can add any two things in there, we can add them up, and that's the same as u minus v. So we don't have to include subtraction. Yes, Ryan. No. Well, there's two products you can do. There's 3 actually products you could do with vectors. So there's a scalar product. There is the dot product, which it gets generalized to the inner product, and then there's an outer product, which people call the cross product. And so that's a different kind of thing. But yeah, it is a product. It's just a different product. Yeah. So yeah, there is a cross product between vectors and two vectors. I think it's one of the things they cut out in this class when it went down to three things. But you'll hit it if you take multivariable calc. So, okay. Which of the following sets of numbers are closed under it? Well, before we move on, any questions about this? Okay. Which of the following sets of numbers are closed under addition, subtraction, multiplication, division, and powers? So these are just general, we're not thinking about vectors here, just the idea of closure. So what it means to be closed is you can take two numbers in the set, you can do the operation, and if you always end up with a number in that set, then it's closed. Like there's no way of getting a number out of that set. You're kind of stuck in that set with that operation. So are whole numbers closed under addition? See a couple people doing this. Ryan says no. Why do you say no? Okay. So they are. If I take any two whole numbers, add them together, I get another whole number. So are they closed under subtraction? No, because I could take 2, subtract 3, and then I get a -1, and a -1 is not a whole number. It's an integer. So you have to include the negative values. Are the integers closed under multiplication? Are the integers, so you have positive or negative, are they closed under multiplication? I see some people nodding their head. Yes, they are. No matter what two values I take, I multiply them together. Because they're whole numbers, they're positive or negative whole numbers. If I multiply whole numbers, I get whole numbers. So they're in there. Are integers closed under division? No. I did make a mistake. Well, that's rational numbers, but they're not closed under division because 3 divided by 2, I get 3/2, or 1 divided by 2, I'm at 1/2. They're not integers. You have to expand the integers enough. If you expand the integers enough so that everything in there is a set that is closed under division, you get the rational numbers. Okay, rational numbers. There. I forgot to put the Q. It can't be 0 here. Someone called me out on that last time. But so if I take any two integers and write it as P divided by Q, then you get the rational numbers. Are the real numbers closed under powers? Powers is a bit ambiguous. So if you just think whole number powers, then yes. But if you include fractional powers, then you have roots like square roots, and you can't take the square root of a minus. Well, you can take the square root of a -1, but that's not a real number. So then you have to include complex numbers, and complex numbers, they're closed to everything. All the operations that you guys know about, the complex numbers are closed in there. So here's a question, something for you to think about. What operation or what can you do, what do you have to do, or what fails with the rational numbers but is satisfied by the real numbers? So I'm going to let you guys think about that. Just what can you do? It seems like once you get the rational numbers, you have about anything, even if it's rational with you, and you throw in the I in there, so you get complex, but A and B are irrational. Isn't that all that you need? So, okay. Okay, let's work on this. Here's two problems. Take a few minutes. First one, let K be the set of all vectors V in R3 of the form that. So we're a three-dimensional vector, X, Y, and Z, but Y has to equal X, and Z has to equal X3. So the question is K a subspace? And then 2, show that the set of vectors on the line Y equals a -3X is a subspace. So start doing what you can with that. You're welcome to work with the neighbor. You're welcome to talk to your neighbor, unless it's about the exam that you've already taken.
extension, right?
Yeah. All right. What does your gut tell you here? Any of you have gut? Well, maybe you've figured it out, but initially, you might look at this and have a gut reaction. Someone said no. Any other initial responses? Once that no got out there, no one else wants to venture a yes. Okay. So my gut says, I don't think this is going to be a subspace because we have linear combinations to work with, but I don't, and I've got a cubic here, so I think we're going to end up being in trouble. But let's check. Does it have the zero vector? Yes, has the zero vector. At x equals 0, then y equals 0, z equals 0. Yep, it is the, we've got the zero vector. Is it closed under addition? So someone said no. Who said no over here? Go ahead. Why no? Okay, so she said this is the same, a very similar example to what was in the textbook where there was an x squared or an x and an x squared, and you end up with a problem where x, like x1 squared plus x2 squared needs to equal x1 plus x2 quantity squared, and they're not equal, right? So you remember that. Way to study the text. Good job. She forgot to do the web sign, but she did the reading. Good job. All right. See, for those of you that were doubters when reading the textbook, you can learn things from the text. So if you think it's wrong, if you do not think it's a subspace, then you just have to find one counterexample. Just show that there's two vectors that you can add together that aren't in this set, that don't have this form. And so if you don't think it is, let's just pick two. Okay, you said 228, 3, 3, 27. You add them together, and we get 5, 5, and 35. That's right. To fit the pattern, 5, 5, 125. So if x is 5, here x is 5. But if x is 5, then for it to be in the set, then this has to be 5 and this has to be 125. So it's nice to think about sets. I'm going to write this in some fancy notation. So this is x, x, x cubed for any x that's a real number. So, okay. And so that's the set. That's what V is. And this is in S. So this is element of. So it means it's in that set. This is an element of S. But this is not an element of S. So, okay. That's enough to show that it disproves it. You can do a general argument. You don't have to. But you could say, I'm going to pick two arbitrary points, two arbitrary vectors in this set, and add them together. x2, x2, x2 cubed. And what do we get if we add these? Okay, are we good so far? Yeah, so far, like the x coordinate and the y coordinate have to be the same. Hey, we're good. But what does this have to be for it to be in S? Yeah, this needs to be x1 plus x2 quantity cubed. That's what it needs to be. But what actually is it? x1 cubed plus x2 cubed. And are those the same? Nope. They're not equal. Yeah, if the x's are both 0, you're good. If one of the x's is 1 and the other x is 0, like there are sometimes, but this has to work for any x value, like for any vectors here. So, okay. Once we showed that it doesn't work with, once we showed that it's closed, that it's not closed under addition, do we have to show that it's not closed under scalar multiplication or everything that is? Doesn't matter, so we can just stop right there. But you could, just to practice, you could say, you could take a particular value and say, hey, let's do 2 times 2, 2, 8. That's the same as, I'm going to do 4, but 4, 4, 16. But that's not 4, 4, 64. So it doesn't work. Okay. Let's go for number 2. Take a minute to work on number 2. Nice. Yeah, that's good. Okay, it says prove it, let's prove it. Okay, so to show, how does it say it here, vectors on y equals a minus 3x is a subspace. I need to show that it satisfies the 3 subspace criteria. So first, is the 0 vector in there? The 0 vector is on y equals a minus 3x. Let x equal 0, then y equals 0. So 0, 0 is on the line. Okay? Yeah, usually I just say this stuff, right? But I thought and I just said it last class, but if you're writing this up on an exam, this is what you should write it down, okay? And on your homework, this is what you should be writing down. Yes? Oh. It does take more time, so sometimes I just say it, but I know that I should write them down sometimes so you guys can get that. Yes?
For the proof, why do you need like the first little paragraph? Why can't you just jump straight to 1, 2, 3?
So you should tell the person that you're writing the proof to, like what you're doing. Like, what are you doing when you're writing down this? Like, you should tell them, like, yeah, give them some idea about what you're going to do. In the same way that you have like an introductory paragraph to an essay, you know, before you dive right into the argument, you're going to give them some intro. So, because if you do this, so notice I stated what I'm going to prove, right? Well, I didn't say it, but I explained what I'm going to do to prove it. There are different ways to prove things, and so there's pretty much only one way with what you know about proving a subspace. But it's nice to just explain to people what you're doing. Okay, so I need to show that x minus 3x is closed under addition. For all x. Notice, so x1, a minus 3x1. So I took what I know about, okay, I took what I know about this and wrote it into vector form. So for any x, I know the y coordinate has to be a minus 3 that, okay? So same thing that I did over here. I took the relationships I knew and just wrote them in terms of x. Okay, yes? Yeah, this is a really nice thing to do if you can. Sometimes you might have two. You might not just have one vector. You might have two vectors to deal with, and then you're showing that it's going to span 2 dimensions, and you have to show that the subspace is a plane. You're going to show so it is a plane, and you have to show that that plane is a subspace. But yeah, like if you had. You probably read about something like this. You'd have like x minus z, y equals x minus z. And so then you'd have like, well, you're dealing with the vectors x, x minus z, and z. And then I can rewrite that as x, x, 0, and 0 minus z, z. So now I have two that I'm working with. And then I'll deal with linear combinations of those. So, okay. All right. So notice if I take an arbitrary one, call it x, plus an arbitrary x2 minus 3x2 equals x1 plus x2, a minus 3x1 plus a minus 3x2, oops, which equals x1 plus x2 minus 3, and I'm going to factor out a 3, and then what did I show there? x1 plus x2. So what form is this in? Yeah, it's in the form of, the y coordinate is a negative 3 times the x coordinate. So which is of the form x minus 3x. It's a little slicker if you write this, if you call all of your vectors, name all your vectors a set, and then you can just say which is an element of the set, or you can just use the element of sign. Okay? And then so third, so usually you don't just dive into writing the proof. What do you do first? Yeah, you do some exploration. You try some stuff out. You might pick a couple examples like, well, if x is 1 and then I get a minus 3, if x is 2, I get a negative 6. You might add those together and see if that's on the line. Okay, I should have done that first. You usually don't. I've already done this problem once. It's easy for me to start writing this out. But you need to convince yourself that it's true and try to understand why it's true first. So you might try, like, I saw some of you write down this right here, okay? Like trying stuff out. Like, oh, I didn't see a lot of you write this down. So don't think like, boy, other people writing that down, I'm pretty stupid. I didn't think about that. No, don't think that. So yeah, they wrote down this much. It's good. They're trying stuff out to see what it is. And then that's going to be an important part of your argument. How would you test out this? If, like, not what I'm going to write down in the proof, but how would you test out to see if it's closed under scalar multiplication? Molly? Molly has a different question. What's your different question? That's fantastic. She said, what if you did a proof by contradiction? Sure. Go ahead. That's awesome. So if you've had a proof class or if you had a really good math teacher in the past, they may have taught you proof by contradiction, and you're welcome to do that too. It's a way of proving, it's a way you assume something isn't true. Assume that it's not a subspace, and then you have to show that if you assume it's not a subspace, you actually end up with a contradiction. So you showed that it's not false, so it must be true. So yeah. Okay, so like both sides here, or like in here? Yeah, so let's pick, is 3 times this of this form? What? Yeah.
So 3 times that matrix is a number. If you put a number in there, does it fit in the original? Yeah.
Oh, you're trying to plug 3 in here?
No, you plug 3 into the other one.
What do you mean the other one?
The one where you multiply by 3.
This one?
Yes. And then
Like plug in 3, 3? Oh.
Number, right? You get an x. So you put an x value there. And if that x, y coordinate that you get out is in the original, then closed by scalar multiplication.
Okay. So I just picked x equals 1. So I'm just exploring. I'm going to say, hey, I'm just going to pick one vector I know there. I'm going to multiply it by some number. And, you know, just to test it out, and I get 3, -9. Is that on this line? Is it of the form the y coordinate is a -3 times the x coordinate? Yeah. I might try another one if I'm not sure. Like maybe I was just lucky, you know. So maybe I'll pick 1.5, a -4.5 multiplied by 2. You know, you could pick something else. And then, yeah, so you can see that, hey, this pattern seems to hold. Then you can do it for something general. So you can do, I'm going to pick any coordinate. I mean, yeah, any coordinate for x. So y is a -3x1. I multiply it by 3, but I'm not going to multiply by 3. What do I need to do? Multiply by any scalar. Because if you pick the wrong scalar, you might be in trouble. Like if you pick 1 or if you pick 0. Sometimes maybe 2 will be a problem, but so then that's going to be Cx. This will be C times the -3. And if I pull out that -3, I rewrite it this way. Thanks. Okay. Then is this of that form? Yep. The y coordinate is a -3 times the x coordinate. So now that I've explored, I can now actually state it. So 3. To show that this set, or the line, whatever it is, I did it just to show that x over -3x is closed under scalar multiplication. Notice, and then I have this thing. Notice that, which is of this form. Oops. X minus 3x. Done. You know what they write at the end of proofs when they're done? They either do therefore, sometimes they'll do this for therefore, but therefore, and then you restate it, the set of vectors on y equals -3x is a subspace. But you can also just write q dot e dot d. Quod erat demonstratum. It's Latin for, which is like the thing that was to be demonstrated. So, what? Oh, or draw a box. Right, so that's the end. Draw a box, boom. So, but you might hear people say QED, meaning like I just proved it. Like that's the end of the argument. Maybe you guys don't hear that, but okay, don't hang around mathematician stuff. All right. Oh wow, that took a lot longer than I thought. Okay. One thing I just want to emphasize at the end here that if we're answering questions, I can't remember what this was, 3. Is 212 in the row space of A? We call this A. The book says, oh, the way you answer this question is you augment it at the bottom and do row operations. And if you can do row operations with these without swapping out that bottom row and get that bottom row to be 0, 0, 0, then it's in that row space. But the book also has to be careful and said, well, you actually have to be careful in what you do here. You can only use the top row you can only use rows above it to change the rows below it. Yeah, it says that in the book. And you're like, so what we do is, and you're not, well, you can switch the order maybe, but anyway, you can end up with problems that way. So what you really shouldn't do this. What you should, because you can accidentally make errors, or you have to be more careful. What we do is just transpose this whole thing. So turn your rows into columns, turn your columns into rows, 2, 1, 2, and then you just do your regular row operations, and if this is consistent, if there's at least one solution, then this is in the row space of this. But then you don't have to worry about those, that special, well, I can use this one to change these, I can use this one to change this, but you can't use these lower ones to change the one above it. And so don't even worry about that. Just do it this way, okay? So we're answering, the question we're answering is the transpose of this in the column space of this transpose. And that's the same as saying, is this in the row space of this? So, okay, have a great day. QED.